Hello, everybody. Well, this is it. This is our last lecture. And we saved, I guess, the most important thing for last. Well, I guess most important thing besides the Earth. The sun. The solar system. This is the name of our class, the system of the sun. So let's talk about the sun for a little bit and end the class this way. And right now, here, if we were in the classroom, we'd be hearing Here Comes the Sun by the Beatles. But guess what? I didn't have it on here. It's not the PowerPoint, it's the PDF. And we don't have it. And that was actually, it sounded pretty good in the classroom. I just want to tell you. So sorry about that. So what do you need to know about the sun? Well, take a look at the sun through a filter. And you have something like that through a special filter. And again, it's a big ball of gas. It's about 100 times the diameter of the Earth. And let's see what you need to know here. 93 million miles from the Earth. Yeah, that's always good to know, 1 AU. Here's something you don't have to know. 1 second of its energy, if you could harness just 1 second of all the energy that was released from the sun, you can get the energy needs for the United States for 90,000 years. We don't even harness the energy that's hitting the Earth. I mean, a lot of it goes to waste. All right, but you don't have to know that. You don't have to know that, but just know a lot of energy coming from the sun. Light from the sun gets to the Earth in 8 minutes. Nah, you don't have to know that. It means it's 8 light minutes away. Here's something that's good to know. It's mostly hydrogen, with helium next. You don't have to know the percentages, but it's about 74% hydrogen, 24% helium, and 2% other gases. Has an 11-year cycle of sunspot activity. You might as well write that down. What else? Don't worry about the 22-year cycle of magnetic activity. Don't worry about that. Is 5 billion years old. That's good to know. We think it's 5 billion years old and maybe another 5 to about maybe 7 billion years left. All right. Now, anything here you need to know? I would say that the mass of the sun is called 1 solar mass. That's good enough. No, it's big. It's good enough. Regions of the sun. Don't write these down yet, but we're going to talk about each one and give you kind of talk about what's going on in each of these regions. All right. Nothing to write down here, but the sun is said to be in hydrostatic equilibrium. It means that the pressure, the forces compressing it, which is gravity, gravity's compressing it, but there's forces pushing out, and it's balanced. So that's called hydrostatic equilibrium. Now, write this down. Photosphere. It's the part of the sun you see with your naked eye. But of course, never stare at the sun with your naked eye. Always use a filter. It's about 11,000 degrees. I'm not going to have you remember that. But the two things that are happening in the photosphere, two things that are good to know, the two major occurrences. One is called granulation. One's called sunspots. Now, here's a picture of iron gas, a filter, just taking a picture of ionized iron. So the sun has a lot of different gases, mostly hydrogen and helium, but there's iron gas in there. So this is an enhanced picture showing where there's the hottest iron gas being shown here. And granulation. So let's talk about what that means. Kind of like when you're boiling let's say your pasta, and you have a rolling boil in your pot. What happens is the warmer water rises, and then it cools, becomes more dense, and it sinks. So the warmer water, or even if you're talking about a gas, warmer gas will rise like a hot air balloon. So what happens in the sun? It's like it's kind of like a rolling boil, but not with water, but with gas. Kind of like in your pot of pasta, warmer water rises, cools, sinks. So you get a rolling boil. There's actually a rolling convection of gas, where the warmer gas is rising and then cooling off and then sinking. So if you see these brighter areas, that's where the gas is rising. The darker areas is where it's cooling off and sinking. And these granules are about the size of Arizona. Every little mottled little speck there is about the size of Arizona. So it's like gas in this rolling state of convection, where rising and falling. So that's called granulation. Sunspots, good to know what those are. Sunspots are darker, cooler areas on the sun. The sun has a very strong magnetic field. It gets twisted and warped, and certain gases are kept up from falling, and they cool off. So what happens is that you see these darker areas, and that is just gas that is cooler. It's not being allowed to fall back down, to heat up again. So because it's cooler, it's not giving off as much light, and it appears darker. So sunspots are just darker regions on the sun because they're cooler by about 3,000 degrees. So make sure, yeah, that's a good thing to know. If you were to take one of these sunspots and move it to the side of the sun, you'd say, wow, it looks bright. It only looks dark compared to the brighter, hotter rest of the sun around it. And these things can last, these sunspots can last several hours to several months, and they're usually larger than the size of the Earth. Now, I don't have to know this, but they kind of taken on the name, like we talked about shadows. The darker region is the umbra. The around is called the penumbra. I'm not going to ask you that. But look at this. Some real pictures. There's the edge of the sun called the limb of the sun. Look at these sunspots. There's the umbra, the penumbra. These are the size. These are bigger than Earth, these darker areas. Now, sunspot cycle. Turns out that about every 11 years, there seems to be a lot of sunspots. And then it kind of dies off after a while, and about 5.5 years later, there's not that many. And then another 5.5 years later, there's a lot. So it's called the sunspot cycle. It has to do with the magnetic field on the sun, or in the sun, I should say. And so the sunspot cycle is about 11 years, 11-year sunspot cycle, from maximum to maximum on average. That's good to know, 11-year sunspot cycle. Now, one time, between 1645 and 1715, you don't have to know this, it's called the Maunder Minimum, because there weren't many sunspots seen, and in Europe, it was very cold. It was called the Little Ice Age in Europe. And so the sun's activity really affects the Earth's weather. And we're not even sure in all ways that it does, but it does. But turns out when there weren't many sunspots, it was very, very cold on Earth, at least in Europe. And I'm sure it was cold other places too, but this was recorded in Europe. Butterfly diagram, don't worry about that. It just shows if you chart the sunspots over time, it kind of takes the shape of a butterfly. Not going to ask you that. Now, here's something good to know. The sun exhibits differential rotation. We talked about this with like Jupiter and Saturn, even Uranus and Neptune. It means because it's a big ball of gas, different parts rotate at different rates. And you don't have to know the numbers here, but the sun, because it's gas, is not all rotating at the same rate. It turns out that the rotation at the equator is about 25 days. So it takes 25 days. The sun actually rotates, spins. And at the poles, it's slower. It takes about 35 days. So the equator is rotating faster. It takes only 25 days than the poles. And again, it's a big ball of gas. Differential rotation. Good to know. Sun, differential rotation. It's like a big Jupiter. Magnetic field lines represented here. You have a sunspot pair. There's a good tidbits chapter to read about sunspots and the sun, so make sure to do that. There's a north polarity, south polarity for sunspots. Look at this. Here's actually, I think, a prominent scene. This was a video, but it's not anymore. The sun in ultraviolet light, different types of light. And here's the sun with an ultraviolet filter. Chromosphere, write this down. Actually, I never mentioned this, but the photosphere meant the sphere of light. You don't have to know that. The chromosphere is above the photosphere. It's a part of the sun above the photosphere. Again, it's just gas. It's the sphere of color. A lot of X-rays from the chromosphere. The chromosphere. We could see it during a total solar eclipse that we talked about in some of the last lectures, and that's where the prominences are. So very thin. So just don't you don't have to write anything down here. It's where helium was first detected in 1868 in the chromosphere. I'm not going to ask you that. So a couple of things I want you to write down for what's going on in the chromosphere. Flares and prominences. It's good to know. Don't worry about spicules. So flares and prominences occur in the chromosphere. Spicules. Don't worry about that. Little spikes are fingers of gas which extend up into the corona of the sun. But flares, here's what I want you to know. They're like these explosions which release light, different types of light, X-rays, high-energy particles, protons, electrons, and can disrupt radio communications. These flares, usually happening around sunspots. So there's just a burst of energy, a flare, and what these can do, enhance the auroras. These particles from flares come into our atmosphere along the magnetic field lines very close to the North and South Pole, and we get the aurora borealis, the northern lights, and the aurora australis, the southern lights. So it's particles from the sun hitting our gases in our atmosphere, causing it to glow. That's what the auroras are. Auroras mean lights. Now, prominences. These are arcs of hydrogen gas leaping up along magnetic field lines, which you can see during a total solar eclipse with your naked eye. But normally you can't unless you have a special filter to see these. So those are prominences. People look at these and say, oh, look at those flares. There's a flare. They're not flares. When you see them along the edge, they're called prominences. Those are arcs of gas extending millions of miles into the corona. And again, it's not flames. Sun is not burning. There's a nuclear reaction. It's not the same thing as like burning a piece of paper. Those are not flames. It's hot gas, but not flames. Here's a NASA Solar Dynamics Observatory. You don't have to write that down. But look at this shot with different filters, getting into the sun, prominences, and just beautiful. Corona, this part out here. Look at that prominence. A sunquake, 11th magnitude. I don't know how they figure out the 7th magnitude. So there's vibrations in the sun. I guess they call those sunquakes. Not the same kind of thing as like, well, kind of like an earthquake, but you're talking about it in gas, not in Earth. Look at this one. Here's a satellite. This almost looks like a phoenix or like a person kind of coming out of the sun. You see like a head and like almost like wings. Great looking prominence. That's just beautiful. Corona. Good to know that. Corona meaning crown. It is only visible during a total solar eclipse. It's the outer atmosphere of the sun. Very low density, but it's actually hotter. The particles are moving faster in the corona, the gas atoms, than in the photosphere or chromosphere. So if you have a fast-moving gas atom, it means it's a high temperature. But there's not much heat there because it's so thin. So the atoms might be moving fast, but there aren't as many atoms. But during an eclipse, this is a terrible picture again. I mean, you can't get a good picture of a total solar eclipse. You have to see it with your own eyes. And look at that. That's a corona. The color is just that's terrible here. In reality, it's a color you can't even, like, it doesn't exist. That color does not exist in human language. You have to see it to experience it. But there's the corona, the outer atmosphere of the sun. Look, some terrible pictures of a corona. Again, when you see an eclipse, then you get to see the real thing. But here's some artificial, that's an eclipse happening, but here's some artificial eclipses created so you can see the corona, the outer atmosphere. That's a neat picture. I'm not even sure what satellite took that. It might have been the Trace satellite, the sun and the corona. Just beautiful. All right, the solar wind. All the solar wind is particles emitted by the sun, protons and electrons, and these are going out through the solar system. And they actually create the tails of the comets, create the gas tails, the solar wind. So that's particles coming from the sun that head out towards, to even the outer part of the solar system, the solar wind, particles. Yeah, I don't know what that says solar wind here, but I don't see any solar wind. I see the corona. Now, coronal mass ejections. I don't think I'm going to ask you about these, but you might have heard of these. They're from the corona, where because of the magnetic field, there's bursts of energy. And this energy comes out it says billions of tons of plasma, which just means a hot charged gas. And these bursts of energy come out. They can really kind of mess up communications on the Earth. They can, garage doors opening and closing on their own. They could do things like that. Radio communications shut down. One time, the city of Quebec in Canada was a blackout. There was a blackout in Quebec, and they attributed it to a coronal mass ejection. Comets. Remember, the solar wind causes the gas tail here of comets. That's what causes. That's all I need you to know for that. Now, the core of the sun. It's good to know about the core. The core is where the action is. The core is about 25 million degrees Fahrenheit. The core is very dense. A cup full of core gas would be 75 pounds. And what I'd like you to know is this. That's what's going on in the core is something called hydrogen fusion. Now, if you ever take Astronomy 3, you'll learn more about this. But you guys don't have to take Astronomy 3. You've taken Astronomy 4. So something called hydrogen fusion, where hydrogen nuclei slam together because it's so hot, and where protons slam together, same thing, and create helium. And gamma rays are released. Gamma rays, the most energetic type of EMR, of light. And here's the process. You don't have to really know this. But in hydrogen fusion, you have hydrogen slamming together, and gamma rays are released, these little particles called neutrinos. But this is good to know. There's even a chapter that talks about this in the tidbits, that hydrogen fuses to helium and gives off gamma rays. That little symbol means gamma rays. So write this down. Hydrogen fuses into helium and produces gamma rays. And it's the gamma rays that power the stars, powers the sun. So this is just talking about if you can do fusion on the Earth, you can take just a little bit of hydrogen, like what's in water, like a little bit of water, and you can get, just if you were able to fuse it, you can get energy for 35 years for your house, no PG&E. Well, we've never figured a way to do this very efficiently. Some scientists in the 80s said they did cold fusion, never could repeat it. Today, however, we're starting to get energy from fusion, little fusion reactors. We're kind of creating stars in the lab that's actually producing energy by fusion, not by fission like nuclear reactors, but by fusion, where you're slamming smaller nuclei together to create larger nuclei. Now let's talk about the fate of the sun. A star's fate is determined by its mass. Now what's going to happen to the sun? Here's what's going to happen. Now it's called a main sequence star. When it runs out of hydrogen in its core, it's going to swell up and become what is called a giant or red giant. And then because of other fusions happening around the core, it's going to eventually become what is known as a planetary nebula. It's going to burp off its shell of gas. The core is going to be left over. And the core is going to be called a white dwarf. So the sun is going to swell up. It's right now called a main sequence star. Most of its life it is. It'll swell up when it's dying and become a giant, envelop the Earth probably, if not get very close to enveloping the Earth. Anyway, the Earth's going to be too hot, regardless, for us to live on. But that's not for, this is good to know, 5 to 7 billion years from now. We still have 5 to 7 billion years. Well, they say we might have only a billion years before it gets, hotter on the Earth because of the sun changing. But really, the sun's not going to die for 5 to 7 billion years. So we have some time before the sun becomes a planetary nebula and a white dwarf. No. So I don't ever like this slide, but look, this is called the Helix Nebula. This is what the fate of our sun's going to be like. It's a planetary nebula. This is called a planetary. The name is the helix. There's the core, the white dwarf, which is actually a carbon core that's left over by a star, by a low-mass star. So we think this is going to happen to the sun in about 5 to 7 billion years. So that's it. That's the fate. And I don't know if you've ever seen this. This has nothing to do with really anything we're talking about. But the green flash, when the sun sets and you have a nice flat horizon, you'll see a flash of green. I don't know if you've ever seen this. When it sets right at the ocean, and usually it's the ocean where you see this best, where there's because of diffraction of light or refraction, they'll never really explain this, but there's a flash of green called the green flash. So this is just to get your mind off that the sun is going to die in 5 to 7 billion years. And we're going to have to go somewhere to avoid this. So the green flash, if you don't like thinking about this, think about the green flash. Because the green flash is nicer. And that's it. That's it for this semester. I enjoyed having you guys in class. I wish we could still be in class. But unfortunately, we're stuck doing this. So maybe things will get back to normal soon, hopefully. There's no baseball, no basketball. Things are not good. I mean, I know other things. I mean, of course, people are getting sick and everything, but yeah, it's just not a good time. So hopefully we get back. Everybody heals up, gets back, and hopefully maybe I'll see you guys again for a real class that's in person, like Astronomy 12 or Astronomy 3. But if not, good luck with everything. Hope you're hanging in there. And hopefully during the summer things will improve, and during the fall things will get better, and you guys will, go on and have a good time with whatever you do. So take care of yourselves. And that is it. Signing off, Astronomy 4.